This is the lesson for Chapter 2, Lesson 2, Modeling Distributions of Data, focusing especially on normal curves, which is that bell shape. When you think normal, think capital N, think that bell shape. So our key question, what does it mean for a distribution to be normal, and how can this provide us with additional information about our distribution? So a density curve, a curve that lies entirely above the x-axis and has a bell shape to it, is described by a normal curve. To describe a normal curve, we only need two aspects. Mu, its mean, and the standard deviation to know how spread out and what it's centered around. A normal distribution will always be centered around the mean. It'll be symmetric. So if we put a mirror down there on the mean, the left and right of that would look the same. The standard deviation would then tell us how spread out it is, meaning how it would either be fat and short or skinny and tall. A small standard deviation would make it skinny and tall. A fat standard deviation would make it short and fat. So a normal curve is symmetric. Review the normal curve applet that we looked at in class. And then here's also an interactive normal curve here that you should check out and is going to be really helpful for computing area from z-score and vice versa. So this could be useful in class too. Let's take a look at it. So we can use this to interpret our 68, 95, 99.7 rule. 68 means from -1 standard deviations, one standard deviation below the mean. The mean, remember, is 0. This is the z-score for the mean. So one standard deviation below to one standard deviation above, 68% of our values will lie within -1 to 1 for z-score. 95% will be -2 to 2. And this actually gets more exact. It's not quite 2. For about 68% to be -1.96 to 1.96. So 2 standard deviations is an approximation. And we can look down on this to see 95% of our values fall in between -1.96 and 1.96. So that leaves a lot of area, a lot of our values within 2 standard deviations, not even 2. So if 95% are in the shaded area and it's symmetric, that means I have 5% left. 100 minus 95 is 5. If it's symmetric, that means 2.5% of my values are here in the left side of the tail, and 2.5% of my values are here. If we extend it all the way to 3, -3 to +3, so within 3 standard deviations of the mean, we'll have 99.7% of our values. So very interesting, very useful when we're using these to know that. You'll be able to say what percentage of your values fall within that, and we'll see how that is useful as we go forward. So refer to this website. You can type in different z-scores. You can look at intervals between. You can look at it outside, meaning to the left and the right of the value, above, below. So this makes it really easy. And remember, mean would be 0, and standard deviation would be 1 if we want it to be a z-score. You can do area from a value, or you can do value from an area, like if you want to know what z-scores correspond to a certain percentage of scores. So this will be very useful as we go forward. So here we go. If we have a normal curve with a bigger standard deviation, it would be shorter and wider. A smaller standard deviation would lead to a taller and more narrow curve as seen here. So here's 2 different curves, one with a larger standard deviation than the other. So that's what I meant about how the standard deviation changes the shape, kind of stretches it out and brings it down if we have a bigger standard deviation, taller and skinnier if we have a smaller one. So 68, 95, 99.7 is key to understand. And that means that 68% of observations will fall within 1 standard deviation, meaning plus or minus a standard deviation. 95% will fall within 2, so plus or minus 2 standard deviations of the mean. And 99.7% will fall within 3. Now, this describes distributions that are exactly normal. And these are approximations here. We saw in the applet that it's actually 95% corresponds to plus or minus 1.96. The z-score of 1.96 and -1.96. But that's very close to 2, so we use it as a nice approximation. Real data aren't usually exactly normal anyway, so it'll be kind of a ballpark estimate and approximation. So take a second, pause, and go to page 114 to look at these 2 graphics. They really give you a nice picture of what we mean by the borders of 68% being 1 standard deviation, 95 being including the lighter turquoise part, and 99.7 including this darker turquoise part. Meaning most of our values fall within 3 standard deviations. 0.015 would fall out here and 0.015. So like we would have 0.15% on either side because it's symmetric. So we can really do a lot with this in figuring out where things lie. Here's a notation we use for normal distribution, with mu being the mean, standard deviation being sigma here, which tells us how spread out it is. We can define any normal curve with those 2 aspects, since those are the only things that change the shape of the normal curve. or change the height and width, that is. Remember z-scores that we've been talking about are how far our data point is for the mean in terms of our standard deviation. We call this a standardized score. So it's standardized because it tells us in terms of standard deviation. So relative to its own data set that which it came from, what's the z-score? So after this little section, I'm going to ask you to pause again to look in the back of your book. In fact, pause right now, open to the back of your book where you find Table A, and take a look at it, and then start the video again. Table A is areas under the standard normal curve, and the table entry for each z value is under the curve to the left of z. So what we can basically do is take the value here we see for the curve. So for a quick example, a z-score of 0.72, I'd find 0.7 in the z column. I'd go over to 0.02 because these headings represent the hundredths value, so 0.72 would be here. And the values corresponding to the left, it tells me the area to the left is 0.7642 or 76.42%. That means 76.42% of the values in the curve are located to the left or less than a z-score of 0.7. For 0.91, I would go find 0.9 here. It lines up with 0.1 here. So 0.8186 would be my value. That means 81.86% are to the left or smaller than 0.91. And that could also let me figure out how many are bigger by subtracting it from 100% or one whole. So 1 minus this value would give me area greater than that value of 0.91. So very useful. Keep in mind that this area is always the value to the left. There's always a drawing on there, so always refer to that so you don't confuse whether it's less than or greater than the z-score. Check out the normal curve calculator function on 118 to 119. We're going to start to use that a lot. We'll get slightly different answers whether we use the table or the calculator, but they'll be very close. Again, when we perform these calculations and solve problems, we're going to use state, plan, do, conclude. One way you could remember that is the SPDC, Statistics Problems Demand Consistency. Not my favorite acronym, but maybe it helps you. State the problem in terms of the variable of interest, so defining the variable, state what it is we're trying to answer. Plan by drawing a picture of the distribution, meaning draw the normal curve, shade the area we're interested in. Do, that means perform any calculations, find the standard score, z. When we say standardize x, that means to calculate z, the standard score. Use table A and the knowledge that the area under the normal curve is 1, just like any density curve. Or you could use your calculator. Then conclude by answering the stated problem in context of the problem. So by directly saying what it means in terms of the variable we're talking about, x, and the answer to our problem. State, plan, do, conclude. Quickly familiarize yourself with the technology corners in this because they'll be very helpful and they'll make your work much easier. So go to 118 to 119 and 123 to 124 in your book to look at z-scores to areas and vice versa. They have the printout of the calculator and a nice description of how to use it. So let's look, pause, and then come back once you've seen how to do that, and let's look at how we assess normality. We never assume that a distribution is normal unless you know it for a fact. If there's skew, or there's multiple peaks, or there's no bell shape, then we know it's not normal. So any skew, any multiple peaks, or not bell shaped, then it's not normal. So we have to have a symmetrical, unimodal, bell-shaped curve. Then the 68, 95, 99.7 rule can provide evidence. Also, we can test using that. So if that works out for plus or minus 1 standard deviation, plus or minus 2 standard deviations, and plus or minus 3 standard deviations, then we know we're good. Normal probability plots are described here. They're not going to be a big focus for us because they're not included on the AP test. But we can do a normal probability plot to see if we get a straight line in order to tell if we have a good normal distribution. Inverse norm will be very useful for us. So be very familiar with calculator functions and really take the time to learn them. They'll make everything on quizzes and tests in your project much easier. So take a second to pause. Here's your multiple choice. Pause it here. Read over the summary and look over examples in the book so you get a good sense of how to use table A, a good sense of how to use the calculator functions, and then correctly interpret the 68, 95, 99.7 rule. What do we mean in terms of 1, 2, and 3 standard deviations for the mean? Keep in mind that all these are approximately, that's why that's there in the answer. So what do we mean by 1 standard deviation, 2 standard deviation, and 3 standard deviations from the mean? Pause now, read over the lesson in your book, look over the summary, and then answer this multiple choice question as well as the free response on the Google Doc or the Google form, sorry.